If you recall, yesterday we introduced the idea of a parameterized curve that we're going to start putting into our vector fields. We got to get some practice. We got to learn some parameterized curves that we can identify, just like we have to learn some functions that we can identify. Y equals mx plus b produces a line. Y equals ax squared plus bx plus c produces a parabola. X squared plus y squared equals 1 is a circle, and so on. There are certain equations that we recognize as shapes. There are certain parameterized curves that we need to recognize as shapes as well. The reason that we want to do this is that we want to be able to define a one-dimensional curve running through two-dimensional or three-dimensional space. We've done a lot of work with one-dimensional curves in two-dimensional space with functions and equations. But we also want to learn how to parameterize things in R2, one-dimensional curves in R2, because we'll need that when we start parameterizing curves in R3. As you know, if we take a function, if z is a function of x and y, that's going to produce a two-dimensional surface in R3. That's not what we want to describe. So we can't use a function to describe a one-dimensional curve in R3. That's going to give us a whole surface. Similarly, the equations in x, y, and z are producing surfaces in R3. X squared plus y squared plus z squared equals 1 produces the surface, unit sphere, centered at the origin with a radius of 1. So if we have an equation in x, y, and z, that's producing a surface. If we have a function, z is a function of x and y, which is the usual. We could also write x as a function of y and z and just turn everything 90 degrees. But that's producing a surface. We need to be able to describe a one-dimensional path through three-dimensional space. So our solution is this. Our solution, like I was there. Our solution is this. We'll define x, y, and z independently of each other as functions of some parameter. And then we'll just describe what values of the parameter we're going to be plugging in. So for example, yesterday we looked at the unit circle. Very popular one to look at. The unit circle. Here, a position vector could be cosine of ti and sine of tj. This produced a unit circle for t between 0 and 2 pi. This produced a circle, a unit circle, starting at 1, 0, going around once counterclockwise. So the starting at 1, 0, that's because our values of t go from 0 to 2 pi. So the starting point is when t is equal to 0. It's going around once because we're using all the values of t from 0 to 2 pi. And we notice that the cosine of t and sine of t are both functions with a period of 2 pi. The period of our two functions is 2 pi. So it's less about us going around, the going around once part is less about using t from 0 to 2 pi and more about the fact that we're going, t goes from 0 to 2 pi and the period of our two coordinate functions is also 2 pi. That's what's making us go around once. Counterclockwise has to do with how we define the 0 and the positive values of t. Counterclockwise business is the cosine starts off at 1, sine starts off at 0. t goes from 0 to pi over 2, going to make things go counterclockwise. The unit circle is because the coefficients of our cosine and sine, the amplitude of our cosine and sine is equal to 1. So that's giving us our radius. So we can make various adjustments to this so we can change our circle around. So for example, if we define a different curve, let's suppose that I change to 3 cosine of t and 3 sine of t. Still for t between 0 and 2 pi. All I've changed is the amplitude of the cosine and the sine. So instead of a circle of radius 1, we have a circle of radius 3. It'll start off at 3, 0 and go around once counterclockwise. I just changed the amplitude of my sine and my cosine and my sine. But I didn't change anything else, so all the other stuff stayed the same. So if we have my cosine of t and sine of t, and I set my window up for t to go from 0 to 2 pi, the t step is just how often it's plugging in values of t. We get our circle of radius 1. If I go in and adjust and say 3 cosine of t and 3 sine of t, there's my circle of radius 3, goes around once counterclockwise, starting from 3, 0. So if I start adjusting now notice that I changed both amplitudes to 3, and so that maintained a circle. If I just change one of the amplitudes, let's say I have a 3 cosine of t, but then I adjust my sine of t coefficient to be 2. Don't change anything else. So in the x direction, we'll have a radius, not really going to be a radius anymore, but we'll start off at 3, 0 and go down to -3, 0. But in the y direction, we'll only go up to 0, 2 and down to 0, -2. So we're going to end up with an ellipse. So if I change my y equals, if I trade my 3 sine of t, cosine of t, and I go 2 sine of t, that's going to give us an ellipse. So notice that it squashed it down. It's still the same width, but the height is shorter. We're creating an ellipse. Because that's all that an ellipse is. Actually, that's all that a circle is. A circle is just the same in both directions. An ellipse, one of them is squished. So let's go in and change some other things. What if oops. Let's keep this 3 cosine of t and 2 sine of t j. And let's change the values of t that we're plugging in. Let's say t is going to go from 0 to pi. Notice that I adjusted the values of t that I'm going to plug in, but I didn't change the period of cosine of t and sine of t. I still have a coefficient of 1 on the t. So the period of those two functions is still 2 pi. Take a moment and think about what's going to happen if I only plug in values from 0 to pi as I go into my machine and make some adjustments. First, I'm going to turn off these. So now my minimum t is 0 and my maximum t is pi. Let's see what happens. Pretty much as expected. We got t equals 0 to t equals pi. We got the upper half because I changed the values of t that I'm plugging in. I'm only plugging in that first half circle, but I didn't change the period of my two functions. I don't know why in the previous one I felt the need to shout ellipse. So now I'm going to change something else so we can see some other trig stuff that's going on. A lot of times our trig review shows up when we least expect it. So now I'm still going to have t go from 0 to pi. I'm going to maintain that. But I'm going to go in here and put a coefficient of 2 on my parameter. So now I'm still only plugging in values from 0 to pi. I'm still only plugging in values from 0 to pi, but now I've adjusted the function. Take a moment while I'm changing things and speculate what's going to happen. Now we got the whole ellipse again. And that's because we went in and adjusted the period. So this is good news. We can make an entire ellipse with any period that we want. We can choose the values of t that we're going to plug in. We just need to adjust the period of our ellipse or our component functions. Just by adjusting in the component function, we can have whatever interval of t that we want. So that's good news. We could use whatever interval we want and still get the entire ellipse. That's bad news, because we can use any interval we want and still get the entire ellipse. The point is that we're in control. We have a lot of control with the parameters. We can make the parameters whatever we want. 0 to 2 pi might be inconvenient for us. I want to make this this whole ellipse happen, and I want my parameter to be from 0 to 1. Let's suppose that I only want to use the interval from 0 to 1. Let's suppose that we only want to plug in values of t from 0 to 1, but we want to make sure that we graph the entire ellipse. So we know that we can do that. Here's how we get the ellipse. But now we're going to go in and adjust our coefficient of t to make sure that the period is 1 and not 2 pi. So I want the period to equal 1. So if the period is equal to 1, the period is 2 pi divided by that coefficient. So b is 2 pi divided by the period that we want. So I want to use I want my t to go from 0 to 1. And I want to get the whole ellipse. So I'll adjust my coefficient to be 2 pi. That came out really wonky. Why did it come out really wonky? Because I'm not plugging in enough values of t. So, that came out terrible. But I'm only plugging in values of t every 0.13. What if I change that to every 0.1? Oops, many decimal points. Let's just play this. It's only going around in 10 steps. Notice that we can see the 10 steps that we have. Let's emphasize that 10 steps. There's going to be 4 steps. Two steps. That's really not enough. That's just back and forth. That's ridiculous. 0.1, that's only giving us 10 steps going around. Let's get more steps. Seems excessive, but there it goes. That's about as round as we can get on this resolution. Because even though this is better than a Game Boy, it's not much better than a Game Boy. So it's somewhere between Game Boy and Switch. I don't have a Switch, so is the resolution okay? Is it? All right. For something that's modern. Right? The last handheld I played was a Sony PSP, so I think that's older than most of the people in the room. So, but yeah, I mean, I think what's happened is that the technology is, it says, no, the camera is not going to focus on how bad the pixels are. It's like a team up between, it's like the TI-84 is like, oh, don't show how bad my pixelation is. And the camera's like, well, got you, fam. I will not focus. But I mean, you can see it like up at the top where it says radian. That vertical R on the radian, that's how wide the pixels are. That is as small as you can make the letter R, capital R, on this screen. Sorry, TI-84, you're super useful, but your resolution is trash. I'm just kidding. It's got the most important quality. It's good enough for demonstration purposes, right? What more do you want? I'm still convinced that gamers that are like, oh, no, I can totally tell the difference between 60 FPS and 3000 FPS. I can totally tell the difference. I'm like, oh, bullshit. Organic eyes don't work that way. If you do see it, it's probably psychological. So I'm glad that you have it, but just recognize when it's psychological. You know what I mean? And enjoy it now. I have the same issues with guitar players. I don't know, does anybody here play guitar? Do you play electric guitar? It's the same kind of thing with guitar players and chasing tone. They like listen to like oh no, it's got to be this $3,000 boutique amp. I've seen you play. Just get a line 6, it'll be more fun. Just get a modeling amp, it'll be way more fun. This is coming from the guy that not only has the modeling amp, but not only has the modeling amp, but I also got a stupidly expensive tube amp. Like, what am I going to be doing? Playing out anytime soon? At least there's an element of awareness in it. So I got like a 5-watt tube amp. So I'm like, all right, I want a tube amp because purity. But I'm just going to get a 5-watt one because what am I going to do? Playing a show soon? No. Do you know what I mean? I am 100% convinced that my expensive tube amp sounds better. I'm also 100% convinced that it's pretty much in my mind. All right. Especially funny because I got the 5-watt tube amp attenuated down to like whatever the minimum is, like a 1 watt or a 1/4 watt, whatever it is. I'm like, oh yeah, listen to how much better that sounds. But the only people I ask are my other guitar player friends. I'm like, oh, dude, come over and check this out. And so my friend Steve comes over and check this out. Sounds awesome, does it? And he's like, oh, yeah, it does. But I am 100% not going to be asking my wife. I was like, well, doesn't this sound much better? Because she'd be like, I don't know the difference. I think we've been together long enough. She just agreed. She'd be like, oh, yeah, that sounds awesome. Awesome. It's like when I go watch her ride our horse. Wasn't she beautiful today? I'm like, oh, the horse is beautiful every day. It's a beautiful horse. It could be like walking through the arena, like stumbling and shit. I'm like, oh, wow, look how graceful. Because I don't know. You know what I mean? So anyway, I'm glad you were able to get a hold of an awesome graphics card and you're working at 3 billion frames per second, but your brain doesn't work that fast. I'm sorry to report. There is some maximum FPS, and I'm sure it's probably more than 24, like an old movie, but I'm pretty sure that it's not in the thousands. You know what I mean? Like imagine looking around the room. Just think about how your eyes work. Really pay attention to how your eyes work. Go from one end of the room to the other end of the room and tell me you just didn't stop at the objects. So if I pan from that board over to that board, I don't look at the stuff in between. You don't smoothly transition from one thing to the in between. Your eyes pick things to focus on and stop and focus on those things as you move across. Sometimes it's only for a very brief moment, but as I move across, if I go above your heads, then I'm not going to pick out any faces, but I'm either going to see nothing between those two because I just keep moving, or my eyes stop and look at the screens as we go across. The computer doesn't behave that way. The computer just shows you everything as it moves across, but your eyes are just going to pick things out. You know what I mean? It's like when you're watching a movie and the camera switches to first person because it's a horror movie. You're now in the eyes of the killer as it stalks his victim, right? And they go, oh, hey, person I don't know is the killer yet. Come on this way, right? And they're like, they show them in the camera and it's like the camera is the eyes. Like, oh, hey, do you want a soda? And then the camera's like, oh, uh-huh, right? That's not how your eyes fucking work. Next time you're looking at someone and you nod in agreement or shake your head in disagreement, your eyes stay focused. Your eyes are still forward. This is what it looks like when you nod on camera. See, nothing moves. You don't like keep your eyes locked in your head and move them up and down when you nod. Or when you shake your head, you don't keep your eyes forward and move them back and forth. You maintain, you're looking at the person. This is what it looks like when you shake your head. Yeah, I didn't move the camera again because your eyes stay focused on the person. You don't lock them in your head and move them back and forth. But still, filmmakers are like, oh, he's got a nod. Yup. No. Jeez, man. Sorry. Pet peeve. What are we talking about? Oh, yes. Good news. We're going to get what we want out of whatever period we choose. Bad news. We can get what we want out of whatever, sorry, not whatever period, but whatever interval we choose for our parameter. Bad news. We can get what we want out of whatever interval we choose for our parameter. Speaking of gamers, one thing that's kind of important is your new console should be able to play your old games. You get a brand new PS5, the first thing you're going to want to load on it is Skyrim. That's just facts. A game older than your little brother. Looks awful to modern eyes, but you're still going to want to put it on there. I think there's a version of Skyrim that I can load onto my TI-84, but whatever computer I have, I'm going to want to put Skyrim on it. I mean, because it's still Skyrim. Coming up on its what? It's 2022. Coming up on its 11th birthday. That's really old for a game. So we want things to be backwards compatible. This parameterization business should be backwards compatible. Oh, my camera's all jacked up now because I was playing with it. A little bit better. Oh, it turns out the writing is a little bit jacked up. I'm kind of like, oh. I realize I haven't written on a vertical board for a long time, but you can tell new teachers because they're writing on the board, and at the end they don't know how to move their feet and write at the same time, or just write to the end of their arm and then start a new line. So like the lines are like all because they're kind of like leaning away, and so it trails off. So if you see a teacher that they're writing on the board and it like trails off this way, they're either new or nervous or a combination of both. Because when you're nervous, it's really hard to like just write a little bit and then just kind of like take a step and then continue writing. Try it sometime. Really weird. Also, when I go by the STEM Center, you can see it happening even though the screens that you're writing on aren't even that big. It all falls off. You'll notice it next time. You might not have noticed it now. You won't be able to unsee it. You're welcome. So let's suppose that we have a function where y as a function of x. Something simple like y equals x squared. All we have to do if we want to produce this y equals x squared, it's actually easy if y is already a function of x, because we just take our independent variable and make it the parameter. We do have to tell our reader what values we're going to be plugging in, but if we just make the x coordinate t and the y coordinate t squared, then we're just plugging in the x, even though we're technically not plugging in the x. So if x is t and y is t squared, notice that I didn't get much of the graph because right now I'm only telling the calculator to plug in from 0 to 1. If I go from -1 to 1, there I get those x values. This calculator doesn't understand infinity, so I'll just go big. Probably can get away with this. I went too big. I wanted to put 10, put 100. There it is. There we go. Any questions? Now notice that when this parabola showed up, it went from left to right like it normally does. If we don't want it to go from left to right for some reason, I'm going to flip the direction of the x-axis by saying x is -2. I'm also going to cut this size down. That was ridiculous. Now it just shows up going the other direction. So we have a lot of control about how our one-dimensional curves will show up. So this one is a parabola left to right. But if I make this adjustment and trade my t for a -t, this is just going to reflect the x-axis around 0. We also know some other stuff. If I change the roles, if instead of y equals x squared, I write x equals y squared, we know that's a parabola that's going to face open right or left. It's going to be our sideways parabola, be rotated through 90 degrees. So if I wanted to do that, if I switch my t squared and t, we can get our parabola to open left or right. So if I make x the t squared and y equal to t, now I'm getting a parabola opening left to right. Notice that it showed up from bottom going up because I've set my t's to go from -10 up to 10. And if I change the direction, it changes the direction. If I want the parabola on the other side, I can just change the sign of the x's. Any questions? So what we noticed today is that we're producing a one-dimensional curve in R2. That's all we did today. But we're producing a one-dimensional curve in R2 or R3. And the curve has some kind of direction to it. We have a lot of control over which direction we want to go because we have a lot of control over how we parameterize the curve. Any questions? Comment? Deep thought? All right, that's it for today. I will see you all on tomorrow. Everybody have a good day and thanks for playing. Have a good day.